All right, let's start. Hello, everyone. This is Dr. Yuzo, ECE 360 Control System class. And today is our 17th lecture, and we will continue our Locus module and leaving the last part of the lecture for reviewing our midterm 2. Okay. So first of all, can you guys hear me well?
Yeah.
All right, thank you. All right, so let's go ahead. This module is pretty much the concept. Okay, there's no not much, or say very intensive calculation, but we do have some in the examples we will see. But it's mainly about the concept of rule locus. Okay. So I'm presenting some bulletins here. First thing you need to be clear, as we discussed in previous lecture, is the rule locus is path of closed loop transfer function pose. Okay, it's not any other transfer function, but closed loop transfer function pose. And how we study it, or how we sketch it, is using the open loop transfer function. This is very easy to feel confused. We will see how to plot it in details to explain why so. Okay. And third thing is we also discuss the stability. We can judge based on the closed loop pose location in the S-plane. This closed loop pose in the S-plane is actually the rule locus, because rule locus, everybody needs to remember this. So to a system like this, with forward transfer function of G, feedback transfer function of H, this generic transfer function, we are obtaining rule locus by what? By introducing a K constant, right? You give this a K, and then the closed loop transfer function becomes Kg divided by 1 plus Kgh. So how to obtaining a path, or say curve? We are varying K value from 0 to infinity continuously change it. You can imagine once we change the K value, the denominator polynomial of the closed loop transfer function is going to change. You have different polynomial, you have different roots, which are nothing but the closed loop transfer function poles, right? They're going to change. Yeah, your K value is changing continuously, so do those poles locations. Therefore, you are seeing a path, or say forming a path. Okay, this is how we come up with the rule locus. And from rule locus in the S-plane, we are able to judge the stability at different K value, right? Because one particular K value, say rule locus, say if like this, this is rule locus. At this location, we have different what? Because different location is representing different poles, and different poles are the result of different K values. So they corresponding to different K values. Okay. You're not confused. I'm not talking about something like this point, this spot value is equal to K. No. I'm talking about at this location of the closed loop poles, the corresponding to one particular K value. Okay, it's not equals to K1. Just correspond to one particular K value. Okay, this is what I mean. Okay. And based on these concepts, let's actually have a more small example, because recalling last lecture, we had a small example like this. This is the example, small example, is trying to clarify the concept here. So given the rule locus, by observing it, you judge first what each, or say how transient TSTP in the overshoot change from K1 to K2, or say from point 1 to point 2. And this is point 1, this is point 2. They correspond to different poles, and therefore different K values. So from 1 to 2, what's the difference in terms of the TS, TP, and overshoot? We can judge this. And also we can tell a range of K to make the system stable. Stable, how to make the system stable? The criteria is all of the poles, all of them are in the left-hand plane, left plane of the S-plane, right? And marginally stable means what? You have some on the left and some along the y-axis. Unstable system means what? If any, as long as you have, it doesn't matter how many. It doesn't matter where are the rest either. The only thing is, if as long as you have any poles on the right half plane, that is unstable system. So this is what we did last lecture. And now let's have another example. Also try to clarify the concept. Assuming another system, another system. System rule locus even as below. What does it look like is this? Okay, what does it look like is this? This is the x-axis, this is y-axis, and the rule locus is like this. Okay. It looks like this. Remember, rule locus has direction. Direction. This is rule locus. Okay, we don't need to worry about the how to come up with this rule locus for the time being. Okay, we just need to study it. Okay, try to understand it. But if you're saying, once again, 2 points. Okay. This point is correspond to one particular K value. We call it K1. And this point here correspond to K2. And the question is asking, first question, what is the range of K for a stable system? The second question is, again, assuming your rule locus moving along the rule locus from K1 to K2, all transient change. And transient mean TS, TP, and overshoot. We just need to study these three particularly. Third question is range of k value for this is a little bit tricky, called underdamped system. So let's think about this problem together. Okay, let's try to solve this problem together. All right, hopefully you have done the copying. So let's start. So first of all, the range of k for a stable system. How can you make the system stable? What's the range of k to guarantee that? Anyone knows?
Well, R has to be at
R?
least greater than, or sorry, the real axis. Yeah, sorry, not R. The real axis needs to be at least greater than 0 in order for that condition to be stable.
Real part needs to be greater than 0.
Yeah.
Which means the poles fall into the right-hand side of the plane.
Oh, sorry, negative. Yeah.
All right, that's better. That's better. Yeah, that's better. And that's better. So basically, John's idea is correct after my correction, of course. So your real parts of poles need to be what? Less than 0. Not even equal, okay? Not even equal, because if it is equal, it becomes what? Marginally stable, right? So this is the idea. Yeah, this is the idea. Then translate this idea into the solution. Then what's the range of k? Well, look at the variation of the locus. It's moving. Not moving. Is towards left, right? Along this towards left, and then basically you have. I'm using 2 pins. Okay, look at the tip. Look at the tips. So basically, they start from here, moving. Okay, good. Intersecting with the y-axis together, okay, same time, and then they cross it, and then moving, and what happened? Merging here, right? And then what happened is they split it again, towards different direction, and ended by different point. This is how you rate this rule locus. So once again, okay, starting from here, because we have arrows, so you know where it started. Right? So they move with the increase of the k. Okay, I don't take me wrong, because of the increase of k, they're moving. Okay, reaching the y-axis, and further they're moving to intersect with x-axis at the same time, and then they split to different opposite directions, and then ended by different point. Okay, this is how you rate it. But because of this, we can tell this point is what? Corresponding to K1 as well. Because like I said, they're moving what? At same speed. They're moving synchronously. Okay. So how to make the pole fall into the left half plane, right? First, you need your K need to beyond K1, right? After beyond K1, it means it's start to move in the left half plane. And it keep moving to here, and then it split, ended by here and here. So what? We don't have a upper limit for the K to become stable system, right? Because what's the K value at here and here? Anyone knows? Here and here, what's the K value?
Well, it would have to be at least greater than K2, which K2 itself is greater than K1. So,
right? That's right. But These 2 points corresponding to k equals to what? Very good. Kevin is right. Kevin is right. Infinity. Does it make sense? Why there infinity? You're starting from k equals to 0. Remember that? Ended by here. These 2 are ending points. You realize that? These 2 are ending points. Of course, they correspond to k value for ending point, which is infinity, right? Because k varies from 0 to infinity, of course. Does it make sense? As long as you can guarantee your k is greater than k1, which is the boundary, or say each point with the y-axis, stable system is stable then. And how big the k becomes, it doesn't matter. It doesn't matter. You ended by here. You have no chance to further what? Cross the y-axis towards right. You have no chance because you already see the. You have already seen the ending point. You ended by there. Done. Does it make sense? Okay. So range for stable system is k is greater than k1. That's it. Okay, that's it. Good, very good. Okay. The second question is, once again, 2 points. Well, k1 here, k2 here, and move your closed loop poles moving from here to here. How the PS gonna change? Well, you need the equations once again. Okay, you need equation once again. dp overshoot how will they change? Give you kind of 2 minutes. Think about them. 2 minutes, and then we talk together. The first 2 takes you maybe 15 seconds. The rest of the time you can think of the last overshoot. All right, let's take a look. So first of all, the TS, how the TS gonna vary? How about TS?
If the denominator increases, then we should get a decrease in the settling time.
Yep. All right. As John said, because the denominator, which is real part number, is increased. Okay? The real part magnitude, of course, is increasing. It's increasing. From here, move towards the K2, from K1 to K2. Right? STS. How about TP then?
That should increase.
So first of all, the denominator, which is the imaginary part magnitude, is what is decreasing, right? It's decreasing. Therefore, the entire TP value is increasing. The last one is you need to calm down, okay? Little by little. So from K1 to K2, what happened is basically your ratio between the real part and the imaginary part is what? Can you tell? So, or if that is a little bit tricky, you can think in this way. First of all,
bigger, or the ratio as far as real is getting a little bit bigger than the imaginary.
So real is become bigger, right? Imaginary part is become small. So the entire real part over imaginary part, this has become what? Bigger, right? Does it make sense? E to the ratio times pi. Well, pi, we don't need to worry about it. E to the negative, this ratio, and this ratio is increasing. Therefore, the entire overshoot is what? Decreasing. Right? Does it make sense? Any questions regarding the answer of question 2? Any concern? Anywhere we need to discuss more?
This would be under the assumption that we're given a second order system, and these are the second order poles.
That's a very good question, actually. That's a very, very good question. The answer is a little bit complicated. First of all, the given system is not necessarily a second order system. However, many higher order systems can be approximated as second order system. So that's why we are using second order system formula to solve them. And the critical thing is, how can you judge a given higher order system? Is it okay to approximate to a second order system or not okay? The critical thing is criteria. Okay, how can you judge? Okay, this is something I want to leave to maybe next module when we discuss about the design. Okay. Is it clear what I'm talking about here?
Yeah.
All right, thanks. Okay. All right, this is the answer for question 2, and question 3 is the range of K for underdamped system. Any idea? Any thought? Here, first of all, Kevin's answer, K between K1 and K is between K1 and K2. This is the correct answer. Yeah, this is the correct answer. Kevin got the correct answer already. And Sawyer mentioned K just equals to K1. Well, no. First, you need to understand what does it mean by underdamped, right? Underdamped means what? System, closed loop, poles are what? Conjugate complex poles. This is something we learned from time response module, where we discussed the different damping case and the corresponding closed loop poles. Remember that? Underdamped means what? Underdamped means, first of all, the damping ratio is between 0 and 1. Now, this is called underdamped. The corresponding poles, we have what? 2 complex conjugate poles. Is that something knock the door? And with this being said, we go ahead to see, well, we just need to find where is S-plane we are seeing complex conjugate poles, right? So where are they? We obviously want to forget anything before K1. Okay? Anything before K1, as we said here, is unstable. So we forget them. After K1, what it is here, which also means here, and the root locus along the real axis, right? The root locus along the real axis, this part, which means the K is greater than K2. Does this make sense? It's K greater than K2, your root locus is along the real axis. And the meaning also, closed loop poles are real numbers. They are not complex conjugate poles. Does it make sense?
A quick question.
Yep.
As we go from K1 to K2, after it hits K2, does it just move along that real axis line?
Yes, correct.
Okay. All right, that was okay.
Yep, correct. And moving along the real axis, then obviously introduce the closed loop poles are real numbers, obviously. And once again, we don't need to worry about how we sketch, how we come up with this root locus for now. We don't need to worry about that. I mean, we are not even seeing the transfer functions. So we're just observing this root locus, try to figure out something.
So we would assume that this root locus plot has to be from the open loop transfer function, right?
Correct.
And if the transfer function, let's say the system we knew had no feedback, we would also assume that this root locus is exactly the same. The open loop and the closed loop would be exactly the same then at that point, right?
Open loop system. Well, your open loop system, yes. In that case, first of all, I don't understand why you have to have an open loop system. However, second, if you do have it, yes, open loop transfer function is same as closed loop transfer function.
Okay.
Just to make sure your open loop transfer function there doesn't involving a feedback inside, which you are not aware. Just make sure that.
Oh, so if we had let's say G itself had a feedback that was included, and then you wanted to say observe the whole system, but you included the feedback system into say as one G, you couldn't do the root locus of the output of that because there being a feedback that had been summed into G?
Yes, because you're in that way, you're pretty much, your G is a closed loop transfer function then, as you said, including feedback inside. You just want to study the output here. No, this guy is a result of your block diagram algebra, which include originally a feedback inside. So you can't give me the closed loop transfer function in the first place. In that way, I can't study the root locus.
So then what would happen if you had multiple feedback, like inside of G? Like how would you even do the root locus? Because one root locus could be inside, one feedback could be inside of the other feedback. So would this only work if you only had, in this entire block diagram, you only had one feedback system?
No. You can study the multiple loops, but it's up to which feedback you are taking care of, right? If you're taking care of this system, then you are involving this feedback only, and then looking for this entire closed loops transfer function, which is the open loop transfer function of the bigger system. Does it make sense?
Okay. But then why isn't it that we wouldn't want to, say, find the whole root locus of the entire closed loop transfer function like that one that you have above?
No. The root locus is the result of closed loop transfer function poles. No problem for that. The method we're studying or sketching is using the open loop transfer function.
Okay.
Okay, you still need that open loop transfer function to sketch this transfer function. Okay, to sketch this root locus for the closed loop transfer function.
Okay.
And when you program the MATLAB, the same thing. You are using the open loop transfer function. If you're using closed loop transfer function to plot the root locus, is not right. Not right. So here, underdamped system. Between K1 and K2, because between K1 and K2 you have closed loop poles in what? Obviously, this is what? 1, 2, 3, 4, 2 and 3 quadrant, right? 2 and 3 quadrant. Inside of those 2 quadrants, obviously, you have stable, first of all, second, underdamped poles. Right? Does everything make sense for this example? Any questions? All right, if this is clear, then let's talk about the or say how to sketch it. Okay. Let's study this, how we come up with the root locus mathematically in detail. But first of all, you need to understand the so-called properties of root locus. So once again, it is emphasizing the points on the root locus, or say along the root locus, are closed loop poles. Okay, once again, this concept must be very solid, firm. And therefore, their roots of closed loop transfer function denominator polynomial. Very easy to understand. And therefore, there are roots of what? Once again, we recalling this generic block diagram, and the closed loop transfer function of it is nothing but G or 1GH, right? And what we do is introducing K here and here. Okay? So according to this, is pretty much talking about the poles, or say the points along the root locus are what? The roots of whom? How about this? We just assume this polynomial down there, the denominator polynomial. All right. So this denominator polynomial, then what can we know about it? This is a conclusion we can receive. How about that? Simply moving one to the other side of the equal. And the G and H are, remember, they're in terms of S. Obviously, they're in terms of S. We are talking about a frequency domain, S domain, a transfer function, of course. and their function of s equals to 91. Here, let's assume if s is a complex number, because in the rule locus, obviously we have real number. It could be real number, it could be imaginary number, it could be complex number, which is more common, right? So if s is common as a complex number, the entire thing is complex number as well, right? Does it make sense? And complex number mathematically equivalent to what? A phasor. Phasor means what? It means you have a magnitude and a phase angle. And this phasor with this amount of magnitude and this amount of phase angle is equal to -1. And -1 is what? In terms of phasor. -1 equals what? Phasor. Equivalent phasor is what? 41. What is the magnitude? And what is the angle? Anyone knows? 91 equals to phasor. Of course it equals to, because 91 is real number. However, it's special types of complex number. Does that make sense? So it's equivalent to 1 phasor. But I haven't got it. Magnitude of 1. -1's magnitude, of course, is 1. What is the phase angle? As 180 degree. Or -180 degree. It doesn't matter. Right? Positive, negative, 180 degree are same. How about this concept? Is this clear? Okay, 91 equals to 1 angle of 180. Okay, absolutely right. And make it more generalized. How about this? Does it make sense? Because as I said, it's positive, negative, 180 is okay. Then you plus minus more 360 degree, then still the same angle. That's why I'm involving that all of those cases. Is this clear what I'm talking about here? So we give a k, which is integer value, any integer value, times 180 degree, representing the exactly same phase angle. Right? So if this is clear, then what we have is actually two things. Okay. Two things. This phasor equals to this phasor. Now, once again, okay, this phasor equals to this phasor. And what's the conclusion? Two things, right? In terms of magnitude. Is equals what? This guy equals what?
1.
Here we go. 1. Okay. And in terms of angle of it, this guy equals what? Just the angle then. So here, so-called properties. It means magnitude property and phase property. And of course, have you guys realize who is this KGH? Who is it? KGH, we receive two properties, magnitude and phase properties for this KGH. But who is KGH? Anyone realize? Does it make sense? It's nothing but our open loop transfer function. Open loop transfer function. So your open loop transfer function following two properties like this. And this is also telling you what? So the S value to satisfy both properties are what? Closed loop poles. And on the Locus. Does it make sense? Obviously, they're in terms of S, and if you have S value satisfy both properties, this S value is definitely closed loop poles, and also definitely on the Locus. In other words, the points on the Locus satisfy definitely for both properties. Okay, points on the Locus definitely satisfy both. Any questions here? Does it
So
make sense?
why do we use 2k plus 1 in a phase angle?
Say that again.
Why do we use 2k plus 1 in the phase angle?
Like I said, we are trying to involve different, because 180 is okay. 180 is also right? The 180 plus 360 is right too. And 180 plus 360 is right too, right? And 180 plus maybe 720, 180 plus or minus 720. All of these phase angle are identical phase angle, they're same. So to involve all of them, I'm using this.
So is k value is same as k times GSHS?
No, this is a capital K. This is a lowercase k. This is a good point. If you don't like it, you could name this k as any other, say n. Maybe n is better. No, these two k's are absolutely not the same k. Okay, this k is the introduced again. Here, this k is a what? Introduced a new integer number to involve more angles here. Okay, these are not same k. Okay? These are absolutely not same k.
Okay.
So, any other questions? All right, if this is fine, then let's use these two properties, okay, to solve some mathematical problem. Right. We start to have let's main page. Place it here. example 1 here, let's say, given the system block diagram like this, what you want to do is, first of all, check if point -2 plus square 2 over 2j is on the rule locus. Second, if it is, find the corresponding k value. All right, let's solve this problem together. Okay, let's see how to use these two properties. So first of all, how to check? This is a very easy thing, right? You just said the S point, the S value, satisfy making these two property hold true, and that S value, or say the point, is on the rule locus, right? Now it is given this complex number, which is nothing but S value. This is the S value. Is it on the rule locus? What it can we do is using the phase property. Phase property saying here, okay, the second one. Here. So let's try to find KGH first. Obviously, we are looking for the open loop transfer function KGH first, right? According to the given block diagram, what is the KGH? Okay. This is KGH, right? And this is very straightforward. Open loop transfer function. And what matters is what's the angle for it. The angle of these kind of fraction between, or say ratio between two as polynomial equals, anyone knows what is the angle? How about this? Does this make sense? Any questions regarding this? And if this is fine, then let's see what is the angle for each one of them. So angle of K equals to what? Oh, by the way, this angle of a polynomial means the angle of the polynomial. Okay, you just need to understand what I mean here. Okay, this is the angle of K. This is the angle of this S plus 3, angle of s plus 4, and so on. So here, first one, the angle of k equals to what? I know Kevin is right. Okay, Kevin is right. 0 degree, right? Why is 0 degree? No imaginary. Okay, no imaginary. Okay. How you understand a constant? Just like here, just like what we did here. Okay, the -1. So if we, how you understand is like this. Okay, you have S plane here. Okay. Let's say -1. How you plot -1 into S plane? -1 is this is real. This is imaginary, right? Axis. 1 means this is 91. This is 91, right? As a phaser, is pointing towards 91, towards left, or say, starting from the 0 origin point. This phaser, the angle is what? This angle is here. That's why it's 180 degree. This is -1. And what is positive 1? The positive 1 is here. This is a positive 1, right? It's positive 1. The positive 1 is this. This is positive 1. Both blue and red have the same length, which is representing the magnitude. Of course, 91 and positive 1, they have same magnitude. It makes perfect sense. And what is the angle for a positive 1 then? The positive 1, there's no angle between this blue and the positive side of the real axis, so it's 0 degree. And what is k then? Never forget, k is a number, what? Between 0 and the infinity, right? This is how we come up with the Locus. We are varying the k from 0 to infinity, so it's greater than 1. And it might be any number, of course, and the magnitude doesn't affect the phase angle. Right? The phase angle remains as 0, just like a positive 1. Okay? This is how you understand this phase angle of a constant. Okay? Phase angle of constant. Then what is the angle for S plus 3 then? First of all, you substitute S by the given value here. So it's angle of 1 plus square root 2 by 2j plus angle of 2 plus square root 2j. Right? This is nothing but substituting S into the equation here. 0 is 0. This angle, you need to ask for help from calculator. Okay. But how about the very last one? What is the angle for this guy? This is very easy. You come up with the answer right away, right? What is the angle for this guy? This is very
45 degree.
Say that again.
45.
No. 90 degree, right? Kevin is right. Again. It doesn't matter what is the magnitude. This is a purely positive imaginary number. It's along here. It might be this long, might be this long, might be this long. It doesn't matter what's the magnitude. Okay. Magnitude is square root 2 divided by 2. However, its phase angle is from here to here, right? Which is 90 degree. So you need to differentiate the magnitude and phase angle. They're independent to each other. Okay. So 0 and the negative 90 degree here. And the rest of 3 spend like 1 minute use your calculator to calculate what is the phase angle. And here I need to remind you how to do this. Okay, let me use my calculator to give you an example. Because in the past, the students have trouble on this, which is unbelievable to me, but it's very realistic. How to do this phase angle? You're not doing inverse tangent. Okay, you're not doing that. That's not the best way, because it is involving pi in that result. Might mess everything up. How to do this is you input this. Sorry. You simply input this complex number into the calculator. And then click equal. And of course, you end up with this complex number. And then what do you need to do? Do a conversion by calculator. Okay, do a conversion, convert it to polar form. Can you see it? Convert your complex number to polar form. And then you end up with magnitude like this, which we don't care, and phase angle like this. So this guy's phase angle from the calculator is equal to 35.26 degree. This is how you find the phase angle for this. Do the same thing to the rest of two by like a 30 seconds. Go ahead, use your calculator, work on it for this too. See what you end up with. All right, and I see some of you already got the correct answer. So the second one is 19.47 degree, and the third one is 144.70 degree. And then what you need to do is just a simple algebra and sum them up, and ending up with, for this particular problem, negative 80 degree. 180. And make sure your calculator is dealing with this problem friendly, okay? Because many calculators are not in the past, okay? In the past classes, many students complaining $200 TI ones are not working. However, it's not they are not working. It's how you use them. It might coming up with a 180 degree off. So what's the conclusion based on this result then? If it is satisfying the phase property, we can say it is on. Okay. This point is on the Locus. It is. Okay. It's on Locus. 180 is okay. How about if you end up with positive 180? Same thing. Positive 180 is same as negative 180 because they have 360 degree difference. It's the same angle then. Okay. And then next, we're going to use the so-called magnitude property to find the corresponding k value. Corresponding k value. But we can stop here for today and then continue this problem by the next lecture.